Hi everyone, my name is Marilena Pagano and I am the Application Specialist at Hellma. Today I would like to welcome you to our webinar with the NIR specialist Angelo Ferrando on the topic From Idea to Realization, from Laboratory to Industrial Plant, Process Control of Polymerization on a Large Scale. Today's expert, Angelo Ferrando, is working in analytical chemistry for about 20 years. Since 1991, he has been employed at Versalis. In his role as new technological platform head, Angelo is responsible for the development of new technology platforms in the areas of digitalization, decarbonization, and the circular economy. I'm glad he found the time to share his experience with us today. Welcome, Angelo.
Thank you very much, Marilena. The project that is subject of this webinar concerns the implementation of NIR-Technologie on the styrene polymer production facility at the Mantua production site. The projects involve more than 20 measurement points on various plants. Mainly continuous plant. One is a batch process plant. The entire project took about 5 years from the conception to the implementation. The measuring point on the various plants were positioned along the reaction path, mainly. Each measuring point is used for the detection of specific process variables, typically the composition quantities. The process current analyzed consists of organic fluids, liquids, and molten polymer. First of all, I think it's very important to say that a truly essential aspect of the project is collaboration, strong collaboration. It involves many realities, not all incorporate reality, also external realities, which also very different points of view. This is the key of a success of such an initiative, but is also the first difficult to be faced. This must very clear. The idea normally is born in the R&D department, discussed with technology supplier to assess the feasibility, like with Hellma, and then the technology and plant operators are involved to design and implement the application in the field. In the end, the result must be valorized with the product quality manager. The process, as is represented in the slide, is a sort of a circular process, and that is subject to continuous improvement, continuous innovation, and need all the activity for the maintenance of the system. Another aspect is that the project includes 3 fundamental operational clusters, each to be addressed in detail in order to highlight and solve all related or specific problems. This involves assessing whatever and in what terms the evaluation of specific variables is possible, whatever and how is possible to calibrate the instrument, the analyzer, and whatever and how the installation of measuring probes and the positioning of the analyzers needs to be worked on. Well, start about the parameters applicability. When choosing the measurement of one or more variables, one must first define at which point in the plant it is useful and or appropriate to collect data. One must consider what spectral response can be expected for that specific chemical quantity. This will, of course, have consequences for the measurable concentration limits, which must meet the actual process requirements. Other important aspect to consider related to the physical state of the streams, and also the presence of element that could disturb the measurement, such, for instance, relevant presence of water or turbulence that generating bubbles. Here I can show some very essential diagrams of our plants, and the red dots, the red circle, are the positioning of the measurement probes in the most appropriate way in terms of useful significance, technical feasibility, for, in this case, a typically plant for homopolymer or high impact polystyrene. This is in the case of ecopolymer, styrene acrylonitrile, or ABS. We need one more positioning point. And this is for the expandable polystyrene. With one probes in the batch reactor, we have all the information. Go to the spectra. The spectral response in an IR spectrum, and therefore also in an NIR spectrum, depends on the chemical nature of the species being studied. This is very clear. Particular functional groups like carbonyl, oxidryl, and so on, specific hydrocarbon like aromatics of insaturated hydrocarbons or water, have a very strong, very intense responses. It is very useful for our work. The NIR spectrum consists, this is another aspect to consider, of the overtone and combination bands present in the IR spectrum. In this slide, it shows the NIR spectrum of polystyrene in melt state, where is highlighted the significant spectral bands useful for subsequent quantitative calibration. It's very evident that the NIR spectrum is characterized by poor defined signal, very broad, and we will see how this should be considered in quantitative calibration, the spectrum. In this one spectrum, you can see the application about suspension polymerization of styrene. Styrene is in water, and we can see how the spectrum changes the highlight both the significant signal of styrene molecule and very broad, intense water signal, the band in the middle. Here, in a series of spectra, we can see how the monomer signals progressively decrease, and the polymer bands, of course, increase instead. This behavior indicates that it is possible, spectrally speaking, of course, to follow polymerization. It has to determine the conversion of the monomer to polymer. That is the polymerization process. In this series of spectra, we can also see the water signal that also gradually changes. This phenomenon, which is fundamentally linked to the radiation scattering phenomenon, can be useful in estimating the growth of polymer particle size during the evaluation of the polymerization. Well, let's go now to consider the second operational cluster, the calibration. Calibration, the purpose of which is to enable quantitative information to be obtained from the spectrum required, depending on the process stream considered and the variables to be determined. Different situations are possible. In the simple case, it may be possible to produce synthetic samples covering the entire range of expected calibration, while in other cases it is necessary to simulate the process in laboratory. Depending on the number of variables and concentration range, the number of sample required from few dozen to over 100 must be assessed. Another aspect to be evaluated is the possibility of taking sample directly in the plant. This means a dedicated sample socket must be therefore be available. The operation must be guaranteed safe working. Pay attention of chemical hazard of the substances, and the samples collected must be stable in time. Let us now give you a very brief introduction to multivariate calibration, which is necessary due to the presence of broad signal, as said before, in NIR spectrum. The first stage is to collect spectra of sample of no concentration, making a matrix of spectra and relative matrix of concentration. From this collected data, using specific algorithms, typically PLS, the calibration function is obtained. At this point, we move to the validation phase. This means the model must be applied to a new set of samples of no concentration, but no used in calibration. The comparison between the concentration value predicted by the fit log and the no values allows us to assess reliability of calibration. Of course, the last stage is collect unknown samples, apply the calibration function, and obtain the quantitative values for calibrated variables, of course. As said before, the simplest case concerns liquids, stable process stream, liquid stable process stream, with no and very clearly defined concentration. In this case, it is sufficient to prepare an adequate number of synthetic samples in laboratory and process as described just before. However, when the streams are more complex, such as a reaction mixture, where unreacted monomers, solvent, and polymer are present simultaneously, it is not possible to prepare synthetic samples directly. In this case, a laboratory apparatus simulating the polymerization must be available, from which representative samples can be sampled during the test. I need to make a polymerization in lab and take during the reaction the samples. A situation very similar when studying molten polymers, a mixture of molten polymers, for instance. In this case, it is necessary to have a laboratory extruder on which to mount NIR probes and combine spectral collecting during the extrusion and the samples taken. These cases are much more complex and costly to carry out, but often involve very significant streams because it's very typical of plant. Just to example, very few details to show by way of example how to carry out calibration for a polymer melt. It is a very schematic representation of the situation in an industrial plant, a reactor, tubular reactor, continuous reactor, batch reactor, something like this, and where get out the polymer, the finished polymer, and this is the position of the NIR analyzer on melt polymer. This very simple scheme in practically in laboratory is represented in this way. The lab extruder and the probe and the NIR analyzer. These photos show practically what I explained to you by the scheme before. This is the results. The graph depicted here show the result obtained. The variable monitored in this case is the concentration of a specific comonomer in a copolymer, of course. The nominal value is given by the no concentration of feed material, the sharp curve, violet curve. And the estimated value, either directly or averaged over the time to obtain a less noisy curve, obviously have as a delay due to the extrusion time, the mixing time, but correctly follow the no values. Mixing time, in this case, are therefore also well estimated using this setup. In any case, it is essential to remember that calibration obtained in laboratory should still be validated by samples obtained directly in the plant. This step is indeed critical and not always feasible. If it is not possible to take samples in the field for technical safety or stability reason, laboratory calibration remains the only solution. However, it must be considered that the estimated values may be less reliable. It's possible to have a bias and something like this. In such case, it is a question of how crucial it is to have precise values, absolute values, or rather how useful is to have the variation over the time of that specific variable, even net of any bias. Move to the last operational cluster is related to field installation. In this case, a number of technological, mainly technological and operational issues are addressed. The measuring point can be inline or online, depending on the stream. The appropriate probe must chosen, take into account process conditions such as temperature and operation pressure. It must be considered whether the probe installation requires specific solution such as adapters. Finally, the position of the analyzer with respect to measuring probe define the path length of the fiber, of the optical fiber, and radiation transmission. Okay, we can have mainly three kinds of probes, three typology of probes, at least from the leading manufacturers, as Hellma, of course, can work in transmission, reflection, or in intermediate configuration, transflectance. Transmission is the simplest configuration and can usually be used for clean fluid such as liquids. Reflectance is generally used for more critical cases, typically fluids that no allow good radiation passage. Transflectance is a more special case. It is a hybrid between the two previous solutions and can therefore be used for specific fluids. Well, these three photos relative to our plants show the first one a online solution. This means that the probe is positioned in a bypass. This is very useful when it's possible, because it's possible to exclude and maintenance the probe without problem on the process. The second one in the middle is a probe directly installed on the reactor. This is a inline solution, and the last one on the right again is a inline solution. In this case, is probably is possible to see in the photo. We have very few space, and is impossible from the characteristic also of the fluid to put a bypass. I speak before about adapters. These flanges are inserted directly along the process line, and in the middle is positioned the NIR probe. Another aspect very important about field installation, one of the most critical technological aspect, is optical fiber. They differ greatly from those used for data transmission, in that they have to carry a large amount of radiation and are of a much larger cross-section. There are typical two solutions: the monofiber and the bundle. The monofiber is typically used for transmission application as a lower cost and allow even considerable distance between analyzer and probe, even over 100 meters. The bundle solution is typically used for reflection probe, where the signal is significantly lower. I need to have much fiber that carry radiation. In this case, the solution usually, the distance covered in this case usually is less than 10 meters. But what is the effect? The effect of the length of the optical fiber on the collector signal. Basically, longer lengths result in a reduction of collector signal, and also, this is not so obvious, a reduction of the spectrum amplitude. It has an increase of cutoff. It has the unvaluable spectrum. The blue one is less intense signal with amplitude less than the red one. The figure show also how possible space lead to irregularities in the spectrum, the small peaks, negative peaks. I would like to emphasize here the major problem in laying these fibers. The fibers can neither be pulled, must be laid, and they do not allow excessive bending angles due to their cross-sectional area. If a break occurs in say 100 meters of fiber, this can mean having to replace the entire fiber, as the repair is critical and it is not always possible to find the break point. This aspect for us was one of the major problems that we found during the installation. The other aspect is the positioning of the analyzer. It may be outside the classified area, in the safety area, which is the simple solution, but may involve distance too great to be covered by optical fiber. In such case, an ATEX cabinet must be provided to house the analyzer in the hazardous area. Briefly, in the last part of my presentation, I would like to show you some result. In this slide, you can see that the red dots, which represent the values of a specific chemical quantity, comes from laboratory analysis, describe the process in much less detail. Laboratory analysis also have a significant delay time, usually hours. You take the sample, go to the labs, make the analysis. NIR, on the other hand, gives a real-time measurement available continuously. even when or where there are no major fluctuation in the production, NIR allows transition between product grades, in this case is a polymer production, can be captured accurately and in real time, ensuring perfect segregation between different products, reducing the amount of product classified as transient, which usually considered low value product. This is very interesting for quality control and also have an economic return. In this figure, it can be seen how with classical sampling, the corresponding laboratory analysis, even important production regularities, may be not recorded if they occur between two sampling relations, in the quality of the product, which may not be recorded in the production stage, at the production stage, but be problematic for end customer with obvious commercial problems. Shown here is a comparison of product quality control relative to a specific variable before and after the introduction of NIR. The clear improvement quality is evident. The orange curve is almost a perfect Gaussian and significantly narrow and centered on product target value. In this case, it is show how the addition of a component to ensure product quality, having a real-time control with NIR, can be managed much closer to the threshold value, the lower value in this case, providing important saving. The variable monitor here concerning the amount of rubber added to an anti-shock polymer. In fact, while still maintaining the product quality, the final product quality, there is a saving of around half a percentage point in added material, which on large scale production plant brings a significant economic advantage. Finally, I would like to show an application completely carried out in collaboration, with Hellma, both in terms of probes, that is a reflectance probe, and in terms of the analyzer. In this case, it is a batch project, the only one that we have, the production of expandable polystyrene suspension. The NIR probe in this case make it possible to monitor during the evolution of the production batch in real time the conversion of the monomer to polymer, the left plot, and simultaneously the size growth of the particle. This application is subject of a specific application note from Hellma, which I believe Marilena can surely send to anyone to be interested to go in detail. Okay, this brings me to the end of my presentation. I hope I have not bored you and perhaps give you hints for the application in the field of this technology that Versalis believe is of particular value to the chemical industry. Production regularity certainly means economic benefit, but I would also like to emphasize that is also good for environment. Less waste production, fewer plant shutdown, and consequent reduction in energy consumed. Thank you all again for your attention.
Thank you for joining us today. So this was our last webinar for this year. So we are looking forward to the exciting topics and news we have in store for you next year. So the best way to stay up to date is via LinkedIn. So feel free to subscribe. Yeah, we see you soon and Grazie mille, Angelo.
Grazie a voi. Thank you very much to all.
Thank you.